Okay. Um, what I wanted to do today is to talk about again network data. In the previous class, we talked about nearest neighbor methods, where we were again kind of assuming that our uh, rows of our matrix were you know basically a point set. We're basically given points in space and are in feature space, and things like labeling was like reduced to find classification reduced to finding nearby points, regression reduced to finding nearby points. There is a related area of data that is in many ways a lot like dealing with I'll say nearest neighbor methods, that has to do with network data. A lot of things, data in the world, can be represented as graphs or networks. And a lot of the things that people call data science are really working with network data. If we think about social networks, Facebook is a graph where the vertices are people, and there's an edge between it whenever two people have friends. And Mark Zuckerberg has gotten to be very rich by being able to take this network data and try to decide what ads somebody wants to see. Okay, so trying to interpret the connections as data is an important thing. The World Wide Web. Okay, we imagine a world where the vertices of the web are web pages, and there is a directed edge between any page where I link to you. Okay, and again, Google has gotten very, very rich by by analyzing this network data and to help provide recommendations for what web pages you want to see. There are networks that come up in when you're dealing with product and sales data. You can imagine a world where you can have a vertex where for every product and a vertex for every person, every customer, and you can have an edge when customer I buys product J. Okay, this kind of a network can be used for all kinds of things. It can be used for product recommendations, it can be used for marketing. Again, Amazon has gotten very rich dealing with this particular network, okay, and analyzing this kind of a sales data network is important. And there's all kinds of other things. Again, I'm going to show you in a minute a network that comes from a scientific application, where again you have genes. Okay, you're a living organism. You're made up of proteins. These proteins are made of genes. These proteins have interactions between them. You can imagine networks where the vertices are genes and the edges are interactions. Any questions about network data? I'm sure you guys have seen this many times, or certainly are aware of network data. But there are a couple of points I wanted to make about dealing with networks that we'll talk about today. The first is that there is a close connection between what I will say geometric data or point set data and graphs. Okay, namely, if I give you a bunch of points, okay, it is often points in space. It is often very useful to define a graph between them. It could be a complete graph where you have an edge between every pair of nodes, and maybe the weight of that edge would be how far apart the nodes are, the vertices are. It may be that it's a sparse graph, okay, where you only have edges between pairs of nodes that are very close to each other, okay? But certainly you can go from any point set can naturally define a graph. The other thing is that graphs kind of naturally define point sets. We are used to graphs or networks having pictures like this. If we have a picture like that, what does it mean? it means we have given every vertex a position as a point in space, okay, trying to reflect the structure of that graph, okay? And typically you would like, in such a drawing that things connected by edges, okay, are nearby, and things connected by lots and lots of edges are nearby, okay? So there's all kinds of drawings algorithms for constructing two-dimensional drawings of graphs. That's for visualization. But if we think of a graph as being an adjacency matrix, and we do an SVD of it, okay, some kind of singular value decomposition or principal component analysis, we can construct a low-dimensional representation of that network, where each vertex is represented by points. Any questions about that? So everybody should see that graphs and points, point sets and graphs have at the very least a lot of similarities, okay, if they're not exactly the same thing. Any questions? Okay. Now, when you want to talk about graphs, okay, if you want to start talking about graph data, a lot of it reduces to understanding what the terminology is, okay, in a meaningful way, okay? You know what a directed graph means, that an edge from X to Y, if edge has an edge from X to Y, Y has an edge from X, if there's an edge from X to Y, there's an edge from Y to X. Some graphs are directed, some graphs are undirected. Some graph data is weighted, okay, where you have a number associated with each edge, okay? Some of it is unweighted, okay? Some graphs have funny edges, like multiple edges between pairs of vertices. Sometimes there's self-loops. Things that avoid that are simple graphs. Sometimes we have graphs where there is an inherent drawing, like points in a road network. Okay, if the junctions in a network in a road network represent street corners, well, every street corner has a place on the globe. Sometimes they come with this kind of embedding, sometimes they don't. Sometimes graphs are very sparse, meaning they have a linear number of edges. Sometimes they have a quadratic number of edges. And sometimes the vertices come with labels, okay, telling you something like what class the vertex is, okay? Sometimes they are unlabeled, okay? Any questions? So just to play the game, which properties do Twitter have? Okay, all of you, I guess, are somewhat familiar with Twitter, okay? And it would please me just to know that there's people out there. Is Twitter a directed or undirected graph?
I believe it's directed.
It's directed. If, a lot of people follow Donald Trump on Twitter, Donald Trump doesn't follow a lot of people on Twitter, right? So we agree that for Twitter, we've got a directed graph. Is Twitter a simple graph or a non-simple graph? Can I follow you multiple ways on Twitter? Or do you only follow somebody once?
Just once.
Once. And can you follow yourself?
No.
So I think that Twitter is a simple graph. Do we have an embedding of where the nodes in the Twitter graph actually are? Any opinions here? I might say yes. Okay, every Twitter user typically has to list an address or has a location in space, right? And so if you assume that your Twitter account is augmented by where you are, which many people specify, and if not, is kind of implicit somehow from their IP places. Sometimes you can interpret Twitter as an embedded graph. Okay. Is Twitter a weighted graph where you've got a weight between pairs of edges in a node? Weir says weighted, Weir says unweighted.
Is there a special kind of follow? I don't remember.
I would believe that as far as I know, you can just follow someone. So I don't believe you can express your degree of love. Okay, that might be if you had a weight that measured how much you loved, how close you were really to this guy. I think of Twitter as an unweighted graph.
Yeah, I was just maybe if there was like a favorite option.
Okay, is Twitter a sparse or a dense graph?
Sparse.
Dense would mean almost a large fraction of all possible pairs are connected. Sparse would mean that there's a relatively small number of connections. Would you guys think it's a sparse graph or a dense graph?
Sparse.
I think it's sparse. It's not unbelievably sparse, but again, I am proud to say I have 2,000 followers. Okay, but that's a little bit above average, but not. But there are presumably a million, millions or tens or hundreds of millions of people on Twitter. So a small fraction of edges are there. So I am going to proclaim this to be a sparse graph. And in Twitter are the vertices labeled? Is there a property of each Twitter user that is kind of known?
Like their name?
I guess their name is one, certainly their name. And so I'm going to say that there are annotations about the vertex that are there. They aren't really so much weights, okay, but they are more labels or categorical things. I think I'm going to say that Twitter is labeled, okay? So when you are dealing with network data, it is important to make sure you know what the what graph your property is. Okay. Any questions? Actually, let's think now about the same thing of the product customer graph at Amazon. Now, let's say that for every product we know which customers bought it, and for every customer we know which products they bought. Is that a directed or an undirected graph? Any feelings? I'm willing to accept chat comments now. Okay, if people don't want to yell. The product customer graph, directed or undirected? Any feelings?
I believe it's just undirected.
I would say it is undirected. So for Amazon, that one. Is the graph simple or not simple? This means can a customer by itself? I would probably say no. But can a customer buy a product more than once?
Absolutely.
So assuming you're not representing that by account, but by a different transaction, I might say that the Amazon graph looks like that. Is the product customer graph embedded in space or kind of, not really an associated representation there? I might say that probably the customers are probably represented in space. It's less obvious to me that the products are. And so this is probably a little bit of a murky distinction. Is this a graph, where the edges are weighted or not?
They're weighted if you want to weight by like say amount of transaction.
You could represent it by how many of these things did they buy. You could represent it by what was the price paid. Okay, I'm guessing that they probably treat that as a weighted graph. Okay, is this dense or is this sparse?
This should be sparse. People don't buy from every store.
Okay, so I would guess that this is probably sparse. Jeff Bezos would like it to be a dense graph. If it was a dense graph, every customer would have bought every product. Okay, but that's it. And labeled or unlabeled, I think it's fair to say the products have names. The products probably have types. The classes are what you call it. The customers certainly have names. They are probably put into certain categories. I think I'm going to say that. Any questions about that? So I think that it should be clear that when you have a graph data set, you have to understand its basic properties. Once you have network data, one thing you could do is try to do the things that you learned when you took an algorithms class, okay? That you learned about how to compute shortest paths, which was kind of a measure, if you think about it, the distance between two things. We were interested in distances between things when we were dealing with points and nearest neighbors. Dijkstra's algorithm and shortest path has kind of a similar role in networks. There's lots of things that, ways you can view certain data processing, data science things in terms of graph algorithms. I don't really want to overlay that too much. But I will say that later on today, we're going to talk about clustering in graphs, clustering, and a lot of the the concepts that are related to graph theory, things like connected components, and edge cut sets, and spanning trees. All of these things kind of apply in clustering and many other things. Okay, fair enough. I did want to talk about two particular kinds of data science things that are useful to know about, and one of them is Pagerank. Now, Pagerank is a kind of famous algorithm / quantity that that basically asks, if you're given a graph and you're given a particular vertex, the page rank of that vertex in that graph corresponds to the probability that a random walk ends up at that particular vertex. So you can imagine let's say we have a graph like this. If we do a random walk on the graph, if we have n vertices overall, if we just start taking a random walk, starting anywhere, and we walk, what is the probability that I'm going to end up on this vertex? Okay. About. Okay. Maybe it's not so clear. What if I take a random walk on the graph? What is the probability that I will end up on the center of the star? If I'm taking a random walk from any place and I start going let's say I randomly start someplace and I take random walks and then I suddenly say stop. What is the likelihood that I am going to end up at the center of the star?
50%.
50%. Does everybody see that? 50% of the time I'm at the center of the star. Okay. The rest of it, presumably 2 over n minus 1% of the time, I am at this particular, this particular vertex. Okay, so all the other vertices have equal likelihood of being on, and so the other n over 2. One half of the probability mass has to be divided by those n minus 1 vertices. So for any given graph, if we did random walks, there's kind of a well-defined probability that we will end up at a particular vertex, okay, in the limiting case. And the PageRank is trying to capture that idea. And what it basically says is there's a kind of I will say a recursive formula, or it's a recurrence relation. The PageRank of vertex V at time j is going to be, I'm going to sum up over all vertices u such that there is a directed edge from u to v, and if this PageRank is going to kind of reflect what was the probability, if the PageRank j minus 1u was the probability I was at u at time j minus 1, the previous step, what is the probability that I will walk from there to v? My claim is it's the probability I was at u divided by the number of ways I can walk from u to someplace else. And that is the out degree of u. Okay? So basically, if I sum up over all the vertices that come to me, okay, I will get a new estimate of the PageRank. And in general, after relatively few, relatively few iterations, this will converge, and the PageRank at time, j is going to be roughly the same as at j plus 1, j plus 2, and so on. Any questions about that? Does this formula look like anything that we did so far in class? I want to claim that this formula looks a lot like something that we talked about when we were doing linear algebra. Does anyone remember what that is? What was the equation that defined whether or not a, defined eigenvalues and eigenvectors? Okay. It was something like lambda times a vector v was equal to a matrix times vector v. That was kind of what defined eigenvalues and eigenvectors. This was the eigenvector. This was the eigenvalue associated with it. If we think about it, if we have the probability at a particular time, okay, if v was the probability that at a particular time we were at each vertex, multiplying it by the adjacency matrix is basically saying that whenever we have an edge from u to v, okay, we're going to take the contribution of the associated probability. So really what this PageRank algorithm is doing is computing an eigenvector, okay? And this eigenvector, it's actually kind of the, designed to be the kind of most important eigenvector of the graph. Any questions about that? The net result is that this gives us a good way to quantify something about the importance of each vertex to the network, okay? And PageRank is kind of a very valuable single feature of a network, that if I have to have a one-dimensional value of a graph, what would be a weighted, let's come back. If I have a graph and I didn't do PageRank, if I wanted to come up with one feature for each vertex, what would you guys think is maybe the most natural feature of each vertex before you came in here? If you have to have one feature property for a feature of each vertex, what might that be?
This is for the web page for this person?
Well, not saying any network. If you want to come up with a property of every vertex for every vertex in a network, what is the one quantity that is this simplest thing that comes to mind for the property of a vertex?
Its rank. Well, how many outgoing edges it has.
Outgoing at its degree.
Degree, yeah.
Okay. It should be clear that one natural way of measuring importance, which often works pretty well, is that just the degree. A more important vertex will be connected to more things. PageRank is actually generally correlated with degree, but it does something else. Okay, it values having as your neighbors other things that are of high degree or of importance, because you want not only to have a lot of neighbors, but to have a good chance of visiting you, you want those neighbors to be popular in themselves. Okay, and when you take a network and you compute its PageRank, you end up getting, I will say, important things. One thing that we did once was look at Wikipedia and looked at all the people in Wikipedia and said, who were the ones that had the highest PageRank? Okay, when we did this, these were the ones that we saw. And if you look at these, I think all of you will agree. You've got presidents, you've got dictators, you've got religious figures, philosophers. I think everybody here, people will agree, is a major historical figure. With perhaps the one that is most suspicious is this guy Carl Linnaeus. Does anyone know why Carl Linnaeus has the third highest PageRank of all people in Wikipedia? Does anyone know who Carl Linnaeus is?
Taxonomy?
He was the guy who developed the species genera name system that they use to name all forms of all different species. Why was his PageRank so high? Every plant and animal and dinosaur linked to his webpage, linked to his Wikipedia page. Okay, because there were thousands of organisms that he was the one that gave it the classification name. When you limit the PageRank to people, from people to people, instead of just everything in Wikipedia, people like Linnaeus disappears. Okay, and this kind of highlights that if you're going to use a PageRank as a feature to measure the importance of things, it's important that you have the right graph that you want, that is going to basically best reflect what kind of important thing you want. Okay, so when you're trying to run PageRank, the kind of decisions that you have, the algorithm itself is trivial and not really much you can play with, but you can play with the graph. Okay, you can remove edges that you don't think are relevant. Okay, again, with Linnaeus, we removed the edges from non-people. We like better what we saw. Okay, when Google uses PageRank, they would like to remove edges from spam websites. Again, one way that a website could look important is if they make a lot of little websites that link to them. Okay, you'd like to ideally identify suspicious edges and vertices and delete them first. You have to think about what you do in a PageRank thing when you have a vertex of which has no outgoing edges. If there is no outgoing edge except maybe, let's say, a self loop, no probability will ever leak from that vertex. And it will just be all walks will end up there and keep staying, and eventually it will control all the probability there. So typically, you either have to remove out degree zero vertices or add edges to provide a way for that probability mass to exit, okay? And that could be by explicitly adding edges. It could be by allowing random jumps to other vertices. But bottom line, PageRank is a good way to get a feature out of a vertex, out of vertices, to reflect how important it is or is not. Any questions about PageRank? Okay. The other thing that I would like to tell you as a technique for getting features from graphs that I happen to like a lot, okay, is this question of graph embeddings. A graph embedding is a, in some sense, what we would like to do. Again, if you think you're Mark Zuckerberg, you have the Facebook graph of everybody who's connected to everybody else. You would like to use that network as features in a machine learning model to try to tell you who to send ads to. But the trouble is Facebook is a 3 billion by 3 billion adjacency matrix. If you treat this as 3 billion features, my God, that's gonna, that could fit everything. It's too sparse. What would you like to do? You would like to construct a n by k matrix where k is smaller, that encodes a lot of what the the random matrix has, and the adjacency matrix has. One way we can construct this sparse, the lower dimensional feature representation are things like singular value decomposition. This is exactly why we have singular value decomposition, to take a big matrix and reduce it to a low dimensional feature vector. But there are other interesting techniques for taking graphs and reducing them to low dimensional feature vectors. One observation is that if you have two vertices that often appear next to each other on a random walk, or near each other on a random walk, then they are probably fairly similar vertices, okay? And so there are techniques, which I may talk a little bit more about later, that basically will use random walks to gather information about, how often each vertex goes to each other vertex. And from this, compressing it in the right way, you can train an interesting network representation. Okay, here are some examples of what happened when we took Wikipedia. We used this graph embedding technique we had invented called Deep Walk, which is actually now pretty popular, and used it to try to come up with a low dimensional, let's say 100-dimensional representation of all the people in Wikipedia. Now we have every person in the Wikipedia network of what page links to what other page, is now a point in 100-dimensional space. We can use our nearest neighbor methods to look at who is most similar to any given entity. And I find these things very, very evocative. Who is most similar to Beethoven? Other classical composers. What are the nearest points to Mick Jagger? He was a Rolling Stone, a music singer, for those of you who I may be dating myself. He's connected to other Rolling Stones and Beatles. President Obama was linked to other presidents nearby. Physicists like Einstein, the nearest points in space were other physicists. I was proud to say my nearest neighbors in embedding space were the two founders of Google. And again, they are computer scientists, and 2 out of 3 of us are billionaires. Okay, any other questions? Do people see how these kind of embeddings capture similarities? Okay, and it's a powerful way to take a big network and reduce it to small features that are interesting. Any questions? Let me show you one other final idea about how you can take a graph, a big network, and reduce it to a feature vector, okay, of a modest number of dimensions relatively easily. One idea, which may sound actually counterintuitive, but it's surprisingly good, is to take each row of the adjacent, for vertex v1, v2, v3, each vertex, its connections are defined by a row of an adjacency matrix. Suppose we take the dot product of every row of the adjacency matrix with a random vector, a vector of random numbers. Okay, here I have made up a vector of random numbers, some positive, some negative, and I am taking the dot product of this vector with each row of the adjacency matrix. The dot product of these things is going to produce a number. Okay, if the adjacency matrix was 0, 1, and the random numbers are integers, I'm going to get an integer. What's interesting? We can view the the dot product here as one dimension in a feature representation. If I take a particular random vector and I dot it with all the rows, I will get a dot product, which will be, a number. And my claim is that I could view this dot product as a feature of each vertex. Why would multiplying it by a random numbers make an interesting feature? The important thing is that we're using the same set of random numbers on every, when we compare it against every row of the matrix. If we have two vertices with very, very similar adjacency matrices, in this case, they only differ by one value, you would expect that the dot product of v1 with this random vector is going to roughly equal the dot product of v2 with the random vector. So in this dimension, you would expect that things with similar adjacency matrices will be sets of adjacencies will be close to each other. If you have a different, a wildly different set of things that you're connected to, your dot product is likely to be quite different than from the other two rows. And so by doing this thing with k different random vectors, you can produce a k-dimensional embedding of every vertex just by doing matrix multiplication. Any questions? It may be surprising that multiplying by random numbers yields a good embedding, but there is actually some very interesting theory behind this, okay? And there's a famous theorem called the Johnson-Lindenstrasse theorem that says if you take endpoints in space and you project them down by multiplying them by random vectors into log squared n dimensions, nearest neighbors and the relative distance between points is generally going to be preserved. Okay, so this is another way to kind of compress matrices to develop features, to develop embeddings that we can use for our nearest neighbor methods and machine learning models. Any questions about that? Any questions about embeddings? Why this is interesting? Okay, if you found this interesting, which is unclear, and if you are living in Chapin, it happens tonight, I am speaking at, there's some kind of faculty invitation thing at Chapin. So I'll be talking over Zoom there about things related to these kind of embeddings. If you're interested, come. If not, don't worry about it. Any questions about graphs or embeddings or nearest neighbor methods or anything like that before I move on? Okay. What I'd like to now talk about, I'd like to shift gears a little to a related topic that is quite important, is that of clustering. Okay, we've looked at, we're now starting to think of data as points in space. When we talked about classification, there we were we typically assumed we had labels. We knew that some things were cars. We knew some things were trucks. We had a new item. We wanted to be able to tell if it was a car or a truck. In general, we, in a lot of cases, we will have data that can be represented as a network or data that can be represented as points in space. And we don't necessarily have labels, okay? Methods that will try in an unsupervised way to try to find structure in the data are very, very powerful things. These embedding methods I talked about, one thing they can be thought of as an unsupervised form of learning. Okay, take your data, do some processing without really knowing what the right answer is about the graph. Okay, and use that structure to help make better models. Clustering is an unsupervised learning method that is a way of providing a label associated with each vertex, okay? Namely the label, the name of the cluster that it's in. And unsupervised or almost unsupervised methods are very, very powerful in data science. Often if you wanted to build a classifier, maybe you have a small number of examples that you have labeled by a person at an expensive way in a big giant data set. Let's say you wanted to classify tweets into tweets that are happy tweets or sad tweets or something like this. Maybe you could pay someone to label tweets, are they happy or sad? You've got billions of tweets out there to build a classifier from, but you've only got a small number of them that you can afford to pay someone to say it's a happy tweet or a sad tweet. What you might be able to do, though, is cluster the tweets in some kind of feature space. Then assign all the tweets in a cluster, maybe the label of which more of it the labeled examples have. And now you've got a lot of tweets that sort of have labels. By doing this kind of a semi-supervised way, I can get more and more, I can somehow get a large amount of data, okay, that leverages from a small amount of labeled data. Any questions? Okay. So what is clustering? Clustering is the problem of grouping points by similarity. And what is the reason why clustering is useful? Often in any kind of a data set, the elements do come from a small number of types, okay? Or a small number of perhaps sources that generate these things. And clustering kind of groups things by similarity. If these things have kind of a structure, your elements have a natural structure to them, the clustering is what will hopefully recover that natural structure. And when we do this kind of thing, we need to be able to measure this. To do clustering, We need to be able to measure the similarity of items. Similarity is defined by a distance metric, okay, akin to what we talked about when we were talking about nearest neighbor methods. Any questions? So my first question for you is, how many clusters do you see in this point set? Does anybody see clusters? And does anybody want to tell me how many clusters you see?
3.
Different people will see different things. What do you see?
3.
You see 3.
Yeah.
Okay, does anybody see something else other than 3?
I see 6.
You see 6. Does anybody see anything that's more than 6? I see 9 on some level. Okay, I might see 9. What am I 9? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Does everybody see that there some that we again, some people may see 3. If you see 3, you probably saw these ones. 6, I'm not quite sure where 6 came from. Different people, again, I'm not doubting that it's 6. Clustering is an ill-defined problem. That's kind of what I want to make clear from this. Okay? Clustering is somehow an ill-defined problem because it depends upon what you want your clusters for. And it depends upon what, how you see the world. Okay? The claim is that there are 2 kinds of people in the world. There are lumpers, they call lumpers, and splitters. A lumper is going to be happier to say that yes, these 2 things are sort of, yeah, they differ in some ways, but they're really both dogs. Okay? You look like dogs and wolves. Are dogs and wolves the same animal? Type of animal? Well, a lumper would say, yeah, they all got 4 legs, they all got fur, they probably all bark or howl. Okay? A splitter would be one who's happy to make very fine distinctions. No, dogs are things that come out of pet stores, and wolves are things that are in the jungle. Okay? So recognize that that clustering is an ill-defined thing. Doesn't mean it's not a useful thing. Doesn't mean it's not an important thing. And also recognize that when we're thinking about clusters, we often think in terms of what I would say nice, compact. Again, the Platonic ideal of a cluster, I think, are these. These are relatively compact, dense things that are sort of circular. Okay? But recognize that depending upon what feature space you're in, circular clusters are not necessarily universal. I look at this and I see 2 clusters, okay? Even though, one is kind of contained within the other. Looking at this, I easily see 3 kind of groupings of points, but they're not circular things, okay? Any questions about that? So why do we do clustering? I'm going to say that there are several good reasons. One reason is just for understanding your data set. Okay, if I am given a data set of items, one of the first things that I will try to do is do a scatter plot of them. Perhaps a projection into 2 dimensions of a scatter plot of them. So I can see whether or not they're kind of our natural groupings here. Okay, and so one reason is just to sort of understand your data thing. Another thing is that once you have groupings, you can often build different kinds of models for each grouping. Suppose, let's say I take my data and I happen to see that I have a large number of examples. I want to do a linear regression on these points in feature space. if I saw that if I had a large number of points and a small number of dimensions, okay, I might very well, if I did a clustering, say, wait a second, the points naturally break into three different types. Maybe there's men, women, and Martians, okay? And, you might want to build a different model on each of the elements of each group, okay? Maybe building a different regression model on the elements of each group will be more revealing than building a regression model based on any one group, on ignoring the group ID. So breaking them into smaller groups enables us to model each group differently, and that's a powerful thing. The other thing that's good about clustering is that it lets us identify when something is an outlier. This point here, I claim, is an outlier. Why is it an outlier? It's not so, a reasonable definition is that after we clustered the points, this point is far from any of the cluster centers, okay? And that is a fairly robust method for trying to identify whether you've got an outlier, okay? So one possibility is you look for tiny clusters. If this guy's a cluster by itself, it's probably an outlier. Or if you have a cluster and this guy has been assigned to a cluster but is far from the center, it probably is an outlier. Okay, so that kind of analysis goes hand in hand with clustering. Any questions? So what ways are there to cluster points? Okay, what I will say is probably the most popular data science method for clustering points is something called k-means clustering. You tell me at the beginning of the process how many clusters there's going to be. Okay, maybe you think there's 3 clusters or 5 clusters or 7 clusters. Okay, then you pick k points to start and say these guys are your cluster centers. Okay, in general, what are we going to do? We're going to try to go through a process where we are going to, for each cluster set that we have, compute its centroid. That's going to give us a point that represents the elements in its cluster. Okay, and then once we have the centroids that represent the centers of our cluster, we're going to take every other point and assign it to be to the cluster associated with the centroid for which it is nearest. Now we have a centroid and a set of points that are associated with it. By taking the centroid of these points, our cluster center will now move. Well, what k-means does is it goes through this iterative procedure where it takes once you have a partitioning of the points into clusters, you compute the centroid, you then see how far every point is from all the centroids, and assign each point the centroid that is nearest to it. This will presumably change for some points. Some points will change what partition it was in. If so, we keep iterating and repeating until we either get tired of doing this or no point moves. If no point moves, every point is now at its kind of closest centroid, and we have kind of hit a stable state. Any questions about that? So let's just look at an example before I go any further. Here is an example of k-means clustering. We have a set of points. We pick 3 points at random, okay, and say there's going to be 3 clusters, and we are going to, find what was the nearest neighbor. We're now going to assign each point which was the cluster center that it was closest to. If we think in terms of Vornoin diagrams, if I take a look at this example, these are probably the separating lines. This is the separating line between this and this. This line here is the separating line between this and this. Every point that is on this side of the line gets assigned this as its center. That's going to be the blue points here. Okay, every point above here gets assigned this as its center. That's the purple one. Okay, and the things in between were the red ones where it got it. So after our first iteration, we now have every point has been assigned one of the old centers as its thing. Now compute the centroid of each point of a given color. What this does is move the move the centroids. Okay, if we look at this kind of thing, what is the case here now? There's a lot of points over here. That moves the centroid over. Okay, and when we now recompute the centroid, the point has moved from here to there. When we compute the centroid of the red points, okay, because the red points, it will move. Okay, the green points will move. And as we go through this, each iteration, we are taking, we are assigning each point to its nearest cluster center. Okay, now that we have new labels, we are going to recompute the centroid and keep going until we stabilize. And on this particular example, everything ends happily. After a certain number of iterations, the points finally settle to a place where they define the 3 clusters that we think of as naturally. Any questions? There's no guarantee with k-means clustering that you find the best possible clustering. But in general, it doesn't get, in general, it does a pretty good job of this kind of thing. Any questions? What is the running time of k-means clustering? If I have k points, okay, that I've defined that there's going to be k cluster centers, okay, if I've got, for each one of my points, if I've got k cluster centers, to tell which, for a given point x, which one is closest, okay, I'm going to have to do compare something that takes all, a distance calculation, which takes time proportional to the number of dimensions. I'm going to do that against all k cluster centers. If I do that for n points, each round of finding the nearest neighbor is this. If I now have, my points, once I know what the labels are, finding the centroid of that, of a cluster, takes a similar amount of time. The claim here is that this is going to be essentially, if you think about nkd, this is n times d is the size of the input points. K is the number of clusters, okay? In general, we're going to repeat this many times until we converge. The number of iterations can, if you're very, very unlucky, be actually exponential in n, okay? But generally speaking, the number of iterations is small, okay, till it converges, or we can stop whenever we want. And so if we run a world where we run a small number of iterations and we use a modest number of cluster centers, K-means is actually very fast and actually generally pretty good. Any questions about that? So remember this data set that I had, which was men and women in height, weight, space. When we looked with a supervised classifier to try to identify what was the separating line between men and women in this space, this is what logistic regression found, okay? When in an unsupervised way, we just took these points and said, find me two cluster centers. There's one of them, there's another one that kind of best partitions the points. These 2 points, the perpendicular bisector to them, defines a separating line. When we did that, the kind of cool thing is the separating line. When we did this, we did not know which points were red and which points were blue. K-means clustering doesn't worry about the labels, but still, the the decision boundary it found was not wildly different than what you found from logistic regression. In both cases, it turns out that the this region was very much enriched for the number of women, the red points, and this one was enriched for the number of blue points. Any questions? The cool thing here again is that somehow just doing K-means clustering essentially reconstructed the label that was there inherently in the point set. And that's what we want our clustering methods to do. Any questions? Now, what is a limitation of K-means? In K-means, we are given, again, what are we going to do if I'm given points, I'm given a bunch of points. Let's say here I've got X, Y points, okay? The centroid is going to be basically the average of the values in each dimension. This is fine if our data is numerical, but when we have a labeled attribute, okay, K-means that doesn't work so well, doesn't work anymore. What is the centroid? If we have hair color, what is the centroid between black hair, brown hair, and a redhead? Okay. When you've got labels, the notion of a centroid does not work anymore. Okay. But still, so long as we have a distance function between records, okay, where we decide something about what the distance is between a brown hair and a redhead, okay, we can use a K-means thing, okay, if we use the centermost example as the median, the centermost example as the center point, rather than the actual centroid. So if I have records, okay, of the form, where I've got, points, sorry. Suppose I have a world where I've got labels as at least one of my dimensions. If I want to, if these are the 3 points in my particular partition from a K-means round, because these are the ones that are nearest my centroid, instead of actually taking the centroid of this dimension I could look for which point is most centrally located. Okay, namely, I'd like the point that minimizes the maximum distance to all other points. If I have a distance function on points where I have categorical data, then I can find, by just taking a look at doing a distance computation between all pairs of points in a partition, I can find which one is the one that is centermost. And I will use that as my representation for the cluster, okay, even though it is not a geometric point. Any questions about that? Okay. The biggest and most natural limitation of k-means clustering is not needing to know how many clusters I have in advance. Okay, how do I know when I look at a given point set or how many clusters it has? K-means requires me to tell how many clusters I'm going to have at the start of the computation. One possibility, sometimes you know that by eyeballing examples. Sometimes you know that by inherent properties of how many clusters you want. But generally speaking, a good way to get the a number of clusters is to actually run k-means with all different sizes of numbers of clusters. If I don't know how many clusters I have, maybe I should run it with 2, 3, 4, 5, 6. One way I can evaluate how good a cluster is by looking at the mean squared error of the points. If all these points are assigned this as its clustered center, the quality to which that center represents those points can be measured by the mean squared error, or the squared error of all the points in the cluster from it. We could, for any given clustering, if we have the centroids representing each cluster, we could compute as our error metric what is the mean squared error of a point from its cluster center. If we do this with multiple, with multiple different values of k, for each value of k, we're going to get a clustering into that many, into k clusters. We can compute the mean squared error here. If so, we get a plot where, as a function of the number of clusters, what is the mean squared error? Okay. What we would like to find, a good place to stop, okay, is going to be a value of k, probably something like that, where for a small value of k, you get a low value of error. If you have found the kind of natural clustering, if we have a world where there are 3 natural clusters, if I try to cluster it with 2 point centers, I am probably going to do something like this, and there's going to be a lot of error. If I did it with 3 clusters, my error is going to suddenly jump down. If I did it with 4 clusters, what's going to happen? Maybe I will add another cluster center over here and then kind of create a 4th cluster. But that last cluster I add is not going to dramatically reduce the size of the, it's not going to drastically reduce the amount of error. Okay, so we're looking for kind of the bend in the elbow of this curve. Where is it that we have a small number of clusters explains a lot of the deviations between the points. Any questions? For what value of k will we get the least value of the, if we have n points, what value of k will we get the least amount of error with? If I
Number of
really,
points,
what? How many points?
number of points itself.
Yes, if I had every point being the its own cluster center, then the error between every point and its cluster center is 0. If we allow ourselves an arbitrary number of clusters, okay, the error will go to 0. So we don't really want to minimize. The right k is not the one that minimizes the error. The right k is the one where adding more cluster centers doesn't really reduce the error by very much at this point. Any questions about that? Any questions about clustering or k-means or anything like that? Okay. K-means is a good algorithm. This is what happened when I took our example before and I ran it with different values of k. Okay. For k equals 3, it looks like it did kind of what I would have wanted. For k equals 2, it's not clear kind of how you would partition that thing. But this got a sign down here, which I didn't really like. For k equals 4, it happens to have, in this case, divided up, one of these. When I did k equals 5, it happens to have divided up the, that pool of 4. For k equals 6, it looks pretty, I've got 3, 4, 5, 6. K equals 7. Notice here I've got a little bit of a problem. The, these long clusters kind of got split. When I went to k equals 8, I seemingly have more problems. 2 of these things have been split. By the time I get to k equals 9, actually, it does a generally good job with the exception of up here. Because k-means wants to find round clusters, okay? It has trouble with nested clusters. If I take a look at this example, the centroid of the outer points here equals the same as the centroid of the inner points. So it has a hard time trying to tell that around. Next class, I'll talk about some other clustering algorithms that do better when it comes to trying to find long, thin clusters, okay, than something like k-means. Any questions about that? K-means is a good heuristic clustering algorithm. It's probably the first thing you should try to do. If you're not happy with the quality, you can run it a couple of times, okay? But generally speaking, if you want round clusters, once you have an idea of how many of them you need, k-means is generally a good method. Any questions about it? Any questions about clustering?
Yeah, I was hoping you could kind of get into how you handle labels again.
How I handle labels when it came to k-means?
Yes.
Okay, so this is actually, the idea here is when we're dealing with labels, okay, people sometimes don't talk about k-means. They sometimes talk about what they call the k-Meteoroids algorithm. Meteoroids. What is a meteoroid? A meteoroid is going to be the most central point. Okay? So the median, remember, if we take a look at the centroid came from averaging all of the dimensions, right? So again, if I had 3 points here, this, and this, if I did the median, the centroid, I would average the x's, which would probably give me this. I would average the y's, which would give me this. This would be the centroid of these points. Now, sometimes what we're interested in, suppose instead of being interested in a centroid, if you note the centroid isn't actually a point in the data set. Another way we could represent our cluster might be to try to identify which is the point in our given group that is most central. Okay, in this case, I think this is actually it. What am I going to define most central? Suppose we take the distance from this point to all the other points. The furthest point away from it is not that far away from it. What I'm going to claim is the center of a set of points is going to be the point with the property that it minimizes the distance to all other points. In this case, this red thing is a good center because the longest distance from it to anybody else isn't that bad. This guy is not a good center because the longest distance from it to somebody else, okay, is very large. So one way we could represent the center, instead of a centroid, we could represent a center, a cluster by its most central point. In order to compute its most central point, all we need to do is to have a distance function that between any two pairs of points will tell us what that distance is. And then the center point is the one that minimizes the maximum distance. Now, so long as you have a distance function that is well defined on points with a categorical data in it, then you can find what is the most center point, okay? And use that as its representative. So my claim is the problem of doing k-means on points where you've got categorical data reduces to developing a distance function that can tell the difference between categorical data. Maybe if we had a hair color variable, we could have rated it by the distance would be 0. The hair color distance would be 0 if the hair color of 1 equals the hair color of the second, and it could be 1 otherwise. Okay, maybe we would have a more sophisticated distance function that says that, you know, blonde and brown are closer together than red and blonde. Okay, but regardless, so long as you have a distance function that takes into account the categorical labels. Perhaps you did a 1-hot encoding and gave a distance function. Then you can identify what is the centermost point in a cluster, and that will give you the representative that you need for k-means. Any questions about that?
Yeah, I'm sorry. Could you quickly repeat that bit about 1-hot encoding in the distance?
So another way that you could have, again, I want a distance between things. What if my record on you, the data, suppose all I knew about you was your height in inches, 61, and your hair color. If the hair color could have come from blonde, if you had a universe of hair colors, okay, let's say your hair color, the world of possible hair colors was blonde, black, brown, gray, and red. I've got 5 possible values. I could encode the hair color by 5, 0, 1 variables, saying, is it blonde? Is it brown? Is it red? Is it gray? Is it black? Now then, every one of your labels gets represented as a bit pattern where one of these 5 bits is set to 1 and the others are set to be 0. If we represent it as a Boolean thing, the 0-1 encoding means we can compute the numerical distance between zeros and ones. Okay? So if either we can represent the labels by one or more numerical values, or we could just have a rule telling us how to interpret the distance between 2 categorical variables. Okay? So long as we have a distance function that returns a number of how far things are apart from each other, we can identify which of our training points is the most central and use that as a representative for the cluster. Any questions? Okay, we'll talk a little more about clustering next time. In the meantime, I look forward to reading your progress reports, and I will talk to you next time. Okay, thanks a lot.